Welcome. That's good. Recording is in progress, so this was not recorded. Well, it's a pleasure to have everybody here in honor of Karen. And we start with the math. We jump right in with Kevin's talk on the mathematical legacy of Karen.
Okay, well, I guess I should start by saying that I'm a little scared of this talk. So, pretty similar to when I gave my defense and I was roasted for how that went in the practice sessions. So my title of the talk is An Introduction to the Work of Karen E. Smith, and that's important. Well, the key word is this one, right? It's not the only word you could use. I kind of wanted to put invitation to mimic the book, right? Celebration probably is also accurate, but just to tell you a little bit, the next talk by Amela Hochster will also overview some of the work of Karen's, right? In theory, mine is supposed to be a lower level, more approachable, and the fact that Mel is talking about more stuff after me means I don't have to say things. So from my count, I think Karen has somewhere around 60 papers. Right. I hope her website is correct. So
I have no idea. Probably not.
Maybe 28 students, 20 postdocs. Right, so, but I don't think the numbers really do this justice. So I asked ChatGPT to help give me a couple sentences to say more, right? So maybe Kurt listens to this, he really wrote the words, right? So Karen stands as a beacon of excellence and inspiration in the mathematical community, has made profound contributions to both algebraic geometry and algebra, and her work at the interface of these fields has been pivotal in deepening the connections between them. I think all of that is better said than I could have done it without the help of the AI, right? But let's get started. So if at any point you can't read something I write or understand something I say, please stop me. Right, and again, forgive me. Well, hopefully Karen recognizes the theorems and things that I put up here, but I'm not trying or aiming for the most traditional way of doing this. So, okay, here we go. Right, so just to keep things simple throughout the talk, always K is going to be a perfect field. Right, a positive characteristic. That's just the standing assumption. Right, so let's let R be a normal domain, which is a finite type over K, so a portion of a polynomial ring over K. I'll let D equal the dimension of R, right? And right, so omega R here is going to be a canonical module. Right, so I know the backgrounds of many of the people in the audience are going to know many of the things I say today, but I also know there are a lot of students here that maybe have not seen everything. So I'll try and do as much as I can. So you don't lose a whole lot by assuming a little bit. So on the regular locus, just this is the top wedge of differential forms, and that determines what I mean by the canonical module here in this context. All right, so I thought a lot about how to start off the talk, and I learned many lessons from Karen's on how to give talks, and one of them was that you should state the theorem that you want people to remember as early as possible in the talk, right? So here it is. I'm going to write Smith a lot during the talk, so yeah. That's what it stands for. Right, so, and I haven't told you the players yet, but I'll do it. So here, this theorem, which is kind of the unifying thing for my talk, right? What I'll tell you a little bit about is going to say that the test submodule is contained in the multiplier submodule. Okay. Right, so many of the things that I'll say during the talk, at some level, all right, can be viewed from this theorem. There'll be a lot about test or test submodules and ideals, a bunch about multiplier ideals and multiplier submodules, right? So, but let me tell you, this theorem really, right? So, it's hard to know how best to present it because it has so many different flavors and ways that it has been applied over the years, right? All right, so let me tell you a little about it. Right, so we start off with just taking the Frobenius morphism and reinterpreting it. As maybe many of you have seen, as the inclusion of R inside of its p roots. You can also view this as R viewed by a restriction of scalars for Frobenius, which you might write as the Frobenius push forward. And of course, I can do this with all the iterates. Right, and if you do so, of course, you can view Frobenius as sort of a tower in both directions, keep going further and further. All right, so I'm going to spend much of this first part telling you about the test submodule. Right, so here to do that, we need another player. All right, we need to tell you about the trace of Frobenius. Right, so take the Frobenius push forward of this canonical module omega r, or omega r1 over p, or omega r1 over p, all meaning the same thing, right? And duality here, we're working over a nice perfect field, so this is pretty easy. Abstractly gives me an isomorphism here. Between this Frobenius push forward and the Hom from R1 over P back to omega R. As such, I have an evaluation at one morphism, which is called the trace of Frobenius. Okay. All right, so I have this nice morphism from F4 star omega R to omega R. It has many nice properties, but let me highlight just one of them. In particular, it generates the set of homomorphisms from F4 star omega R back to omega R. Okay, so before proceeding to give you more of a description of the objects in the theorem, another example. So another thing I certainly have heard Karen say over and over again in my life is whenever anything somewhat remotely complicated shows up on the board, she immediately wants me to tell her what does that mean for the polynomial ring, right? All right, so let's look at that here. So again, here, let's say R itself was just a polynomial ring. And again, we've taken this inclusion of R and R1 over P as the Frobenius endomorphism. And in this case, this is just again a polynomial ring where the variables are identified with the p roots of the original variables. Okay. So this is a free R module. Rank p to the d. On an explicit basis, if you like, the basis of well, all the monomials here in x1 of xt with roots. Where the alpha i's are integers over p, and they're all strictly less than 1. Okay? So in this case, of course, omega r right, so, well, I'm working over a polynomial ring, so if I just take the wedge of the d of the variables, that gives me a free generator for this guy, right? And I can identify trace. And so I have this free R module rank p to the d, and I can look at projection onto each of the different basis elements, the dual basis vectors, if you will, right? So, and this is identified with projection onto the largest basis element. Right, so projection onto that factor. Okay, so. In some sense, the observation that, well, an observation that leads to this theorem, right? Is the following characterization of the parameter test submodule, right, for Karen, right? So tau of omega r is the smallest non-zero module n, say inside of omega r, stable under this trace map. We want trace f of say n 1 over p be contained back in that. Okay. Of course, maybe the theorem is slightly less impressive if I just give this to you as the definition here, but this is certainly not the original definition of the parameter test module, right? So as I said, Mel, I leave to give a lot more context to this, but let me say just a little more before we go on. Right, so if instead R is complete local, right, we can dualize this statement, right, to get the following. That the tight closure of 0 in HDMR is the largest proper Frobenius stable submodule of HDMR. Okay? All right, and of course, there are many other characterizations that I should probably add to this list here. It's also identified with the kernel, of the map from HDMR to HDMR plus, where R plus is the absolute integral closure. Right, so what I really want to get across is that this is some kind of package, right? So I haven't told you what type closure is, Mel can do that, right? Right, so I don't really want to talk about local homology, that seems hard, Mel can do that, right? So, and I don't want to talk about R plus R either, that definitely is hard, right? So, I'm saving all of that as a package here, right? But the point is that part of the magic of this simple characterization is that it's something that, gives you this characterization leading to these geometric connections that we're gonna talk about. Okay?
Can I interrupt you?
Yeah.
I just wanted to credit Carl too, because I did everything in this dual way that you did in parentheses. Carl dualized it and put it in.
Let me put it also another way, right? So as a student at Radisson, Michigan, I spent all of my time taking all of the things in this context and then translating them over here so that I could do things with them geometrically. Okay, so certainly, as I said, I'm not trying to give the classical approach. I'm trying to give an overview for some of these big theorems. Okay, right, and as I said, Mel will give a somewhat of a more description later, but there will be others too. So certainly, I have no intention of or ability to give an overview for a huge body of work and influence. Okay. But now that I've done this, I can even give you a rough sketch of the proof. Okay. Okay, so, well, I haven't told you what the multiplier submodule is. Let me do that really quick. And again, trying to avoid as many complicated statements as possible.
Sorry, is this the sketch of the proof of the characterization or?
You're right. Thank you, of the theorem, right? What is the multiplier submodule? So this is, well, one quick definition. Is you look at the intersection of the push forwards of the canonical sheaves over all normal proper birational modifications, right? So think of all of the ways of blowing up over and over again so that you start off with something normal here, right? And just look at all those push forwards. They all live inside of the original omega x, omega r, right? And I'm intersecting those submodules, okay? So the proof sketch goes as follows. Right? Frobenius commutes with everything, right? And as a result, the push forward of omega y under, or whatever, is always going to be stable under the trace of Frobenius. Now again, this is definitely not how Karen typed this up the first way. I see no edge maps for any spectral sequence on the board, right? So I invite you to go take a look. And again, these things are, maybe I'm putting them in a simpler way to give you a flavor here, right? But certainly I think this picture has been extremely influential. Okay. Any questions? Okay, so great. And again, Mel will likely, I know Mel will be able to tell you more about plus closure and type closure being the same for parameter ideals and other ways that you bring this for them. Okay, let's move forward. And let me give you a few variations on this theorem. Okay, so This characterization also gives that tau omega r, and well, let me put it this way. Oops. Also gives that this parameter test submodule and the parameter test ideal, which again, in another way of phrasing it, is the annihilator of the difference between omega and tau omega, right, are compatible with localization and completion. Right, so because type closure now at this point is known not to localize, right? So these statements are highly non-trivial and very difficult to write, but again, it follows very easily from these sorts of characterizations. And I can say, I'm trying to summarize a lot also of many papers by many authors, so I'll try and throw some of those on the board. There are ways to say that this characterization, as well as many of its consequences, are extended to, oh, I wrote omega r, but I really want r, to the test ideal, right? I don't really want to go into that right now. Right, so let me just point you towards the paper of Karen and Gennady Lubeznik. Well, they do much of this. Okay, so that's the first remark. Second one. Assuming you have a good theory of resolutions of singularities, this multiplier cell module, whatever you want to call it, or Brought-Riemann-Schneider sheaf is another way it's sometimes referred to, right? Can be computed by just a single log resolution, right? So what does that mean? Now, instead of asking that your modification is normal, I'm going to ask that it's smooth. And I also want that the exceptional set, the place where this is not an isomorphism, right, has simple crossings or locally looks like the vanishing of monoids. Okay. All right, great. In particular, over C. Okay. And so I'll say more about that as we keep going. Okay, so R at this point, the main theorem or the theorem I referenced was all in characteristic P, right? I've started my switch. Many years ago, Karen told me that there are three kinds of people, right? There are those who work over C. There are those who work in a fixed characteristic P, and there are those who work basically over C, but really just for, mod P, work in large P, right? So I want you to sort of keep that perspective as we keep going through. So let me say a little bit of something about the applications of this this result, the first one I mentioned, with reduction mod P. And again, I'm going to play a little loose here. right? So what is reduction mod P? Start off with, say, a normal complex algebraic variety. For now, pretend that it's defined by equations with integer coefficients. If not, you can play tricks to mimic this situation. And when I take those same equations, mod P, they give me a family of positive characteristic models. Okay. And so here is the theorem I'll tell you about. I'll state it in its full glory, right? So at least this direction is due to basically the theorem I just mentioned, due to Smith. And this direction, right, is due to, or Smith plus work of Hara and then Srinivas. Separately. Right, so the theorem is the following: if my complex algebraic variety has something that's called rational singularities, and that happens if and only if x mod p is f rational, for all large p. Okay? Okay, so I haven't defined f rational or rational. And again, I'm trying to do this as quickly and easy as possible. So just for simplicity, we'll use Kemp's criterion. So x is Kolmogorov, and this parameter test submodule is trivial. And similarly over here, right? So Mel can object, but he's not here. So he'll give you a different definition shortly, but x is Kolmogorov. And this parameter test submodule is trivial. Okay?
Kevin,
Never mind.
I'm listening and I'm watching you.
Be afraid.
I think the only right response to that is this. So, okay. Great. So, and let me write one more variant on the same sort of result here. All right. So, that kind of ties everything together. So, if I start off with the multiplier submodule and go mod p, then it equals the parameter test submodule for all spatially large p. Okay. So, in fact, Karen has a paper titled "The Multiplier Ideal is a Universal Test Ideal." So here, this version is the multiplier submodule, universal test submodule, if you will. I was amused to find, as I was reading through many of Karen's old papers, trying to prepare for the talk, that paper was dedicated to Robin Hartshorne on his 60th. All right, great. Right, so, but again, this looks very simple when phrased this way. This direction really does follow out of this containment of the parameter test ideal module inside of the multiplier submodule. Right, so, but it fits into a much larger dictionary. Of singularities across reduction mod P, right? Let me give you some instances of it. right, so this is but one avatar of this dictionary of singularities that show up in characteristic 0 over the complex numbers being related to those defined by Frobenius and positive characteristic. Right, so here we have rational and F rational. Many of these come from the minimal model program and higher dimensional complex birational algebraic geometry. So Kalamata log terminal singularities, log canonical Dubois, right? And we go through, all right? So let me suffice it to
That is
say,
LC.
what?
Oh, I see. I thought it was a K.
Nope, sorry. Log canonical.
Great.
Okay, thanks for that. Okay, and the point here is that for me at least, it's very hard to think about this dictionary without reference to Karen's work. And in fact, you can probably translate and look at many of her results to deal with things in different sides. And she's worked both on individual sides. So there are later talks this week about Dubois singularities, for example, and other things.
But there's a lot of other names in that.
There are many other names, right? Yeah, right? And that's not to say that some connections were known before, but maybe this was among the first massive triumphs in making this dictionary fit together this way.
What are the extra little arrows with the?
Plus Gorenstein means the two sides collapse. Okay, so I put them up there partly because they're some of my favorite diagrams to help mentally keep track of the implications of the various kinds of singularities. Okay. Right. Of course, I could have also put the multiplier submodule and test ideals on the two sides and listed those as well. And the next thing I want to tell you about kind of changes the direction a little bit, but still fits into this picture. To bring up another sort of big thread in Karen's work, I want to do some global statements. So I'm going to talk about some other players here. So I'm going to tell you about
Can I just share a cool thing?
of course.
When I was a postdoc, so I knew that right diagram really well, worked on various aspects of it, all that stuff. And I didn't know the left diagram really, other than the connection between rational singularities. And then listening to people like János Kollár, and I found I could talk to János really easily, just pretending every time he said log canonical, he's talking about F pure. And, it was just amazing. I could pick up so much of that field from János and Sándor Kovács and others. And then Carl came along. He's like me and Sándor's baby. We tried to prove the things that you did in your thesis about.
Yeah, János knows Zoom.
Oh, is he? All right, great. Hey, János.
Okay.
So I had no idea what they meant. I mean, just encourage students not to be afraid of things you don't know.
All right, so again, to talk about another thread here. This definition is also due to Karen. Let's say X is a normal quasi-projective right over K, right? We say that this is globally F regular. I have to write it again, GFR, provided the following holds. So for all affected Cartesian divisors on X, there exists some large integer E such that I look at the Frobenius map and then compose with the inclusion of OX and OX of T, this map splits. And splits here just means that there is an OX linear map from the far right side to the far left. Okay. All right. So again, Mel might give a definition in a second, or whatever. Let me say that. Right, so equivalently for some or equivalently for all ample divisors A on X, if I look at the section ring, Right, with respect to A, those guys are regular, again, another piece of the puzzle on our diagram. And for the experts over here, right, so I'm been sloppy there, I'm gonna be sloppy here with F regular, but here it really doesn't matter, so. Another celebrated paper of Karen and Gennady that for rated rings, we can strong the same. Okay, so, great. Right, so, but the point here is that, right, so I have some definition here, which is filling in a piece of this dictionary on the right side. Let me tell you why it fits into the puzzle by giving something about reduction of P in a second. But two things. First, again, I was amused as I was looking things up, right? So this definition, which has been very influential and is very, very important for moving the minimal model program forward in positive characteristics, in low characteristics, as well as influencing work in mixed characteristic as well. This definition and the subsequent results I'll say in a second came in a paper that was dedicated to Fulton's 60th birthday. Okay, so. All right, so another theorem. Take a globally F regular variety. All right, so let's say this one is projective. And so then let's take L at RT divisor. All right, and first, both of these theorems are going to tell me that I have unexpected or some strict vanishing theorems that I wouldn't get for arbitrary varieties. All right, so if L is an F, then F1 metals have no higher cohomology. And if L is an F and big, you get an analog of cohomology that vanishing here, right? So HIX minus L, right, is 0 for all the lower cohomologies. Okay. And as she says in the paper, these follow for experts by some standard methods or some standard F splitting tricks, just using the definition, right? So the real magic here is that again, I think this is another instance where Karen's providing the intuition, right? That's connecting things in different places. Okay. All right. Let me make a quick remark for this. So this is about vanishing of cohomology. Right? So you could also talk about non-vanishing of cohomology. And I felt like I should say something about another very influential piece of works, couple of works. Right, so Smith and Heery relate some cohomology non-vanishing to understanding the some understanding of the core versus the graded core, or what this looks like for certain ideals in graded rings, right? So kind of doesn't fit in directly with my whole talk here, right? So in the same thread, right? But one of the reasons to do this transition was to say some global statements here, and I think looking at implications of these methods to vanishing and non-vanishing and how to link up algebra and geometry is certainly something that is a thread of Karen's research. Okay, so but I didn't actually tell you why this fits in the dictionary. So before I erase the, let's do it. So, we put down streets next for this, I don't know which one goes first, that seems right, my notes have the opposite, okay? And so what they show is if you take something which is projective log final type over C, I don't really want to tell you what this is, but I'll do it sort of quickly. Right, so this says there exists a KLT boundary divisor. If you don't know what this is, don't worry too much about it. I'm not going to spend too much time on this, right? So right, with minus K plus delta ample, okay, ample Q divisor, right? And so what they prove is then X mod P is wholly F regular. Right? I can say more. There's a variant of this in positive characteristic as well, which is the converse in positive characteristic. I'll relegate that to having you read the paper. I might also mention that this is an open question. Karen, is it a question or a conjecture?
It can be a conjecture as far as I'm concerned.
I
don't
think
mind
that
being
Mel
wrong.
certainly advocates for conjecturing it and its opposite, so, right, so, as you will, it's a question in the paper, right, now whether the reverse holds as well. Okay, okay, so again, this second sort of thread related to the first one was just to try and emphasize that understanding the relationship between the algebra and its implications for section rings and graded rings and global implications is another big thread in this research. Okay. It's sort of hidden over here, but in this paper, one of the big techniques that they introduced in the study of global regularity is the notion of using these divisor pairs and positive characteristic in a systematic way, especially globally. Right? So I want to say something a little bit about that and bring up some other local statements as well, but I don't want to get mired in too many technicalities, so I'm going to do a segment on the simplest kind of pairs and some related results. All right, so these generalized test ideals, I should probably mention Hara Yoshida, Hara Watanabe, and Takagi, but we'll see them here in a second. The case I want to work with is the following. Just take a hypersurface, a polynomial in D variables, right? And these generalized test ideals take a non-negative real number and spit out a variant on these test submodules or test ideals we've been talking about. All right, so for example, I'll give you a definition here in a second. And again, these are not the original definitions, but some simple things we can do here at the board, right? So if T has the form A over P to the E, A and E are integers at this point, then tau F to the A over P to the E is just the image of the following evaluation map. All right, so again, look at the Homs from the polynomial ring 1 over P to the E back to itself, okay? And now, before we had the trace map, which was evaluation by 1, and I have this F to the A to the P to the E sitting here, so this is evaluation at F to the A over P to the E. Okay? Great. So here's a definition that works when t has a very special form, just powers of p in the denominator, and in general. Right, so what do you do for other types of t's? Well, draw the number line. Right, and it's going to split up. Right, and the following set of half-open intervals in such a way that the following holds. So tau f to the t is tau f ci, the t in one of these half-open intervals. Right, and these things get strictly smaller as I jump between intervals. Okay. So roughly speaking, if you know how to do this for all these, you just use this result to drag it down for all of the other ones by perturbing up just a little bit. Okay. These numbers here are called the jumping numbers. The jumping numbers of these test ideals, right? Jans. And so maybe let's do an example real quick. Right, so hopefully one that several other people in the room are happy to see. Okay, so and let's do equals 2. Okay. Okay, so let's try and use our recipe. And again, this really is an observation, at least in the principal case, maybe it predates this, but for arbitrary ideals, it's due to Blickholm, Mustafa, and Smith. Right, so take f to the 1/2 here, and I take my equation. You'll notice that it breaks up. So where I have a bunch of the basis vectors for r to the 1/p over r, and then some coefficients, and this formula, another way to say it, is you just, the test ideal is given by picking out all those coefficients. In particular, this first jumping number here is what's known as the Epter threshold. Right, so, and well, the test ideals are all trivial before this, so for all smaller values, you get just the Pullman ring itself. So this says that whatever the Epter threshold is of this f, it's certainly less than or equal to 1/2. And in fact, the FBT here is shown to equal 1/2, right? And we're getting close to the end of my talk, right? So I don't want to show everything. I want to highlight that you're going to see some things like this later in the week, and that all of what this example is related to a pretty large body of recent work of Karen and many other co-authors. So, so what words did I write down? I pointed at this, and I wrote extremal, many lines, right? And said, we'll see recent work of Adrian and Smith. And then for this one over here, oh, this is now much worse. too many names, right? So, Zybek, what's her, how do you say her last name? That's the other thing I learned. So I always learn how to pronounce names from Karen, and
Oh,
that's
that's
never
pretty
led
good,
me
yeah.
astray.
I refuse to answer any of them.
With Hinkle, Page, Singh, Smith, Rachu, and Witt, all right? Okay, great, so again, lots of good stuff here to see, and some that you'll see later this week. Okay, all right, so but the main theorem of this segment is the following. Right, so, in this context, the jumping numbers of these tau activities, in particular including the active threshold, are discrete and rational. Right? And again, part of what's amazing about their proof of this theorem is that it's really quite easy to describe the proof, right? In taking these roots, or in taking images under these maps, right? This is some sort of Fermi splitting type morphism here, right? You expect degrees to be divided by p to the e. And after some small perturbation, that's basically what happens. You control the degrees of the generators of these test stereos. Okay? Okay. Right. Other remarks related to this theorem. So, of course, to the t is a characteristic p avatar of something else on the dictionary, namely the logarithmical threshold.
Multiplier.
Oh, sorry, multiplier ideal. I jumped the gun, right? Right. And I have a reason for putting this up there. Trust me. I don't just want to subject you to integrals. Right. So here, F is a polynomial with say complex coefficients instead. Right. And again, t is a non-negative real number. Right. So here, the multiplier submodule here of f to the t is the set of all g's, so that this kernel, norm squared of g over norm squared f to the t, right, is locally integrable at all points. Okay? Right, so I could also talk about variance of these jumping numbers for these multiplier submodules. Right, so, and in fact, the jumping numbers of these JF to the T's were first systematically studied by Karen and co-authors, right? And so let me just show you what one of the things they showed. I'll tell you. Right, so the jumping numbers of these GF to the T's are all roots of the Bernstein-Sato polynomial. Right, so I'm not going to tell you what this is, but again, right out of time, we say differential operators, which has been another huge thread in all of Karen's research. And in fact, there's a great survey article trying to explain, right, why you might view some of these invariants as being related by differential operators across different characteristics. Also, Jack, where are you? Any questions about those? He's going to answer in his talk. So I'll give an overview of this segment of Karen's research as part of his talk, right? Thank you. Much better, right? I knew what I meant, right? So, of course, in the study of differential operators, many other things have arisen. So, influential definition of Frobenius or Frobenius finite representation type, right? And the study of the Frobenius push forwards and how they decompose into different modules, which led to things like F signature and many other things. You know, F signature shows up at least in one of the talks later this week, or somewhere. Okay, all right. Understanding those decompositions led Karen and co-authors to do make a study of in the toric setting of finding new rings that they can show have non-commutative Crebit resolutions and various things like this. Okay, and again, all of this is to come this week. Okay, let me say one more here. All these results come down to really looking at, or the Virginie-Settle result and things related to it come down to a good understanding of nice properties of multiplier ideals, right? And again, Karen has worked a lot on each of the two sides of the dictionary and advanced things individually on each of the two sides, right? So here's another one, which you will hear of at least a couple more times. Right, so my name is Colin Smith. Easy to state in this context. Right, so if I take a prime ideal, right, in the following with d variables over C, then the d symbolic power, the md symbolic power is contained in the mth regular power. Right, for all n, and again, this here is, well, one way to say it is the p primary component of p to the md, right? But of course, I could also talk about symbolic powers again by characterizing them in terms of differential operators. So fits again in this idea of understanding properties of multiplier ideal and how it relates to symbolic powers. Okay? Okay, so with that, hopefully you have an idea that there's a lot of stuff that I haven't been able to cover, right? So I think at this point, the left side of the board and the right side, right? All of it is related. There is a very amazing unifying theme throughout, right? So with that, I want to say two things. First, thank you, Karen, for all of your help. Thanks for giving me the chance to explain some of your beautiful results to everyone here, right? And yeah, let's have a great week.
Thank you, Kevin. I know you could have gone on for hours to go, but thank you for stopping at some point. So are there any questions for Kevin? Hey, you stay up here.
I'm not going anywhere.
Any questions so far? But I guess you explained everything beautifully, as usual. And so we'll have a half an hour coffee break, and then after the break, we'll meet back here with the talk of Mel Hoxter, which we heard is present already. So we meet back.
Oh, present, yeah.
Yeah. All right, see you soon.